Looking at the 2021 exam, problem 2, I'm going to start by looking at the diagram and sort of taking a note of principles that might be relevant. I'm not even looking at the questions. I'm just looking at the diagram. A couple of things I'll note. First of all, we have multiple states which we can relate to each other spatially. Point A is h above the bottom of my loop. H minus 2r above point C, h minus r above point B. Furthermore, point A has got a height h above our spring. So, we can possibly think about potential energy as being relevant. I see a spring and I might be thinking spring potential energy. I could also be thinking simple harmonic motion. To the person to whom I'm recording this video for, though, you probably have not yet seen simple harmonic motion, so that's probably not going to be relevant to this question. Lastly, the other principle I'm thinking about is I noticed that we have this loop, so possibly I'll want to think about circular motion, and I do want to remember F centripetal equals mv squared over r. So all of that is said before I even began reading through our problem statement. Now let's read through the statement. So we start off with a block of mass m starts from rest. So I'm immediately going to note that down up there, v equals 0. At point A, travels with negligible friction. And so I'm immediately going to note down that energy is conserved because there's no non-conservative force at play. So it travels with negligible friction through the loop onto a horizontal surface where the block makes contact with the spring, and we're given the spring constant k. All motion of the spring is in the horizontal direction. We're told point C is the highest point on the loop, right? So we're just labeling our points, point P the rightmost point. Express algebraic answers in terms of m, h, r, and physical constants. Okay. So let's begin with part A. On the top below, which represents the block, draw an arrow that represents the direction of acceleration of the block at point B in the figure above. Okay, we're being asked about direction of acceleration. That to me reminds me of one of two options. So far, all you have seen is that acceleration can be found via kinematics or via dynamics. And the natural choice here is probably dynamics. So what we know is that if we are thinking about the forces acting on our car at point B, we've got mg going down, sorry, our block, not car, mg going down, and because we're in contact with the surface, we probably have an Fn, which is perpendicular to it. We could also logic that we are slowing down and therefore have acceleration going down due to gravity. And we are also moving in a circle, so we should have centripetal acceleration. And so if we are trying to illustrate with a single vector, I would just add those together and show an acceleration vector, which points both down and inwards towards the center of the circle. So let's continue to discussing part B. And so part B begins by asking us to first derive an expression for the speed v of the block at point B. And here we have two possible modes of physics to use to analyze this. We know that when we are at point B, we are moving in circular motion, so potentially we might want to look at F centripetal equals mv squared over r. But we also know that we have an initial state that has been given to us, namely, in our initial state. So initial state, we are at point A, and we have an E initial, which is purely potential. It is mgh. We then have a final state, which is at point B. And over there, we have an E final, which consists of mgr, since we're at height r, plus unknown kinetic energy, 1/2 mv squared. And so since this principle will suffice, I'll go ahead and solve. Set our energies equal to each other, since energy is conserved. mgh equals mgr plus 1/2 mv squared. And so going ahead and solving for v, we get v is equal to, our m's cancel out. V is equal to 2gh minus r square rooted. And there we have it. We can now connect this back in part 2 to circular motion. Part 2 is asking us to derive an expression for the magnitude of the net force on the block at point B. As we discussed earlier, we're going to have a force of gravity, mg. We're going to have a normal force, Fn. Therefore, we can say mg is our known force. Our net force should be mg squared plus Fn squared, so that our job is simply to find Fn. Well, let's go ahead and do that. What we know is that Fn acts centripetally, therefore Fn should equal mv squared over r. And since we know v, we can write m times 2g h minus r. I've squared our result for v all over r. And I'll save myself the writing that out in our expression, but we can simplify this by plugging in. So moving on then, let's have a look at part C. Part C is asking us, in terms of R, derive an expression for the minimum height necessary for the block to maintain contact with the track through point C. So going back to our diagram, we're now comparing points A and C. And for a moment, we might think, well, the minimum height is such that our speed should be 0 at point C. So let's go ahead and think about that. Does that work? If our speed is 0 at point C, let's pay attention to what our forces are. We would have mg going down, and we would just be in free fall. So, clearly, to make it through the top of the track, we need a certain minimum speed. And so, if you're unsure of how to do this, at minimum, try thinking about what physics is relevant at point C. The knowledge I have is that we're moving in a circle. So let's see if looking at the forces and analyzing the circular dynamics will be helpful. We've got mg going down at the top. And previously I said maybe that's the only force, but now that we're not moving at 0 speed, we might also have an Fn pointing down if we're maintaining contact with the track. And so we can say that mg plus Fn equals mv squared over r. Now, let's try thinking about what happens when v decreases. As v decreases, the left-hand side of our equation must also decrease. mg is, of course, fixed, so Fn would decrease. Well, what is the lowest Fn can be? 0. And then we would have mg equal to mv squared over r. By the way, if the block, instead of just being a block, had wheels on the other side of the track, Fn could in fact point outwards, and that would change our answer to the problem. But the result we have now is that at point C, v is equal to square root gr, and we now have 2 points of comparison. At point A, v equals 0, and so our energy is purely potential energy, mgh. At point C, our energy is 2 mgr, because our height is 2r, plus 1/2 mv squared. And so now we can put this together and solve for the minimum height that we need. mgh must equal 2 mgr plus 1/2 mgr. M's cancel out, g cancels out, and we are left with h is equal to 2.5r, or 5/2r. So let's move on then to what I believe is the last part of the problem. Part D, well, not quite the last part. It is determined that h equals 0.3 and r equals 0.1. If the block is released from a height greater than found in part C, what would be the maximum compression, X max, of the spring? So, as we can see in part D, with r equal to 0.1, our h min would be 0.25, so h is indeed greater than our h min. And we're asked to find the maximum compression of the spring. Again, let's use energy analysis. We have 2 points of comparison, namely point A and what I will call point D. We know that we will make it through to reaching the spring. Of course, if we were released from below h max min, then we would never make it to the spring. So again, let's do our energy analysis. As before, our E initial is simply mgh. I'm going to work through this symbolically for now. And in this case, our E final, when the spring is maximally compressed, in fact, our final kinetic energy will be 0. So my E final will simply be 1/2 kx squared. We can plug in mg over 2r for rk as given. And we can now equate our two energies, mgh equals mg over 4r x squared, and we can go ahead and solve for x. So moving on then to our last part, we've got a graph of the maximum compression of the spring as a function of height is shown below, and we're shown h min on the graph. So as we just discussed, if we are released from below a height of h min, we never make it to the spring, and thus the spring is completely uncompressed. And bringing back our solution from part D, we can see that our maximum compression is proportional to square root h, hence the shape of the remainder of the graph.